Whenever you are.
All right. Well, thank you everyone so much for joining today. Another Balerion Space Ventures podcast. It's April 20th, and today we're joined with Stef Crum, the co-founder and CEO of Reditus Space, a very cool company that's working on manufacturing in space and having it return to Earth. A new area of space infrastructure we're starting to see, and I'm excited to chat today to learn about all the future potential and opportunity. So, Steph, thank you so much for being here.
Thank you very much for having me. Yeah. On a very high level at Reditus Space, we build reusable satellites to provide people with high frequency access to the microgravity environment or just space for whatever purpose they may need it for. And so what that looks like on a very pragmatic basis is that we launch satellites that stay on orbit for a little while, subsequently have the ability to come back. And then, if all is well, those satellites can then be launched again later.
Got it. Now, reentry has been sort of like an overlooked bottleneck space ecosystem. Can you tell us what's going on and, why we've seen so many things go into space, but very few things come back. What is the reason behind that and how is it changing?
I think on a very high level, the space industry for especially the commercial space industry for the better part of the last number of decades or in its full existence, really the only commercially viable business cases to date have been focused around data, right? Little bits being marked down just because, frankly, that allows you to keep your satellite on orbit. And it is up till now, at least, a use case that has been more easy to achieve. Um, Things like physical atoms coming down has largely been reserved for missions that have a scientific purpose, right? NASA and other government agencies have been the main motivator behind pushing those types of narrative. But I think our philosophy, and I think there's a lot more that are interested within the reentry world, have started to look more at, hey, we do think that there are applications for actual physical parts of the space economy, but that is going to require an infrastructure to bring those things back. And so that is our main pursuit.
And what kind of things get made in orbit, and why do you want to, go all the way to space just to manufacture something to bring it back?
I think the biggest near-term use case that we spend a lot of our time on, particularly with both the researchers as well as the early stage companies and larger companies that are trying to do it, is it's the microgravity manufacturing world. I think most people that are tuning into this podcast will be at least familiar with it on a high level. But in the case that that isn't the case, I'll give a little bit of background, which is when you don't have any gravity within the production process of either a specific type of chemical or a growth of a specific biological structure, it allows you to create different outcomes. And that's a very generalized statement. So I'll give a specific example just to make that a little bit easier. One of the main applications for it is crystal forming. And so when we all look back to what we learned in high school, particularly related to our carbon structures, you can think about, hey, in when a specific type of carbon structure is created, the absence or presence of a certain amount of pressure results in, on the one side, we create graphite, right, pencil lead, and on the other side, you have diamonds. In a very similar sense, the absence or presence of gravity just creates a different chemical structure, which in a very similar manner just creates a different crystallized outcome. And in certain cases, that can be pretty trivial and it doesn't really do anything else. But in other cases, it can be very similar to the difference between graphite and diamonds, the difference to a type of semiconductor substrate that's all of a sudden tremendously valuable, or it can be a novel type of pharmaceutical crystal. On a very high level, it is more, there are a lot of specific applications for it, but the fundamental thing that you care about is being able to alter physics to just create different outcomes within chemistry.
Got it. And, you know, having these new types of capabilities in space, like what does that really unlock? Like what's the market look like realistically, 5 to 10 years from now with this ability?
I think from our perspective, the main really interesting inflection point is going to be, and we start seeing this happen now on the ISS, and I think Varda is probably the biggest story related to this, which is as things kind of turn from a research application, right? Oh, we're trying to figure out what type of novel structures, what novel type of chemistry we can create. We start looking at, oh no, we've now found something that is valuable enough that it is worth a repeated, frequent trip into that microgravity environment to bring it up and back consistently at the frequency that is appropriate. And so when I look at, hey, what does this look like in 10 years? I think it is about a space infrastructure whose sole focus and job it is to build um, vehicles that are able to just bring mass up and down as efficiently in terms of dollars per kilogram as we possibly can. Uh, that combines both a lot of launches as well as perpetually larger vehicles and potentially things that remain on orbit perpetually.
Got it. And with launch costs, continuing to fall, it's getting cheaper. We're starting to see a lot more players come into just space ecosystem as a whole. So, you're not the only return company, and there's several others that are all talking about it. Few who've actually done it. And, that next level where everyone has operating companies that are both putting things up and bringing them back down. What needs to happen for that environment to change and for that to really begin? I mean, is it like an FAA thing? Like I'm thinking about the logistics and having things return to Earth. It's not a very common thing. So what needs to happen for that just to become the norm?
I think the biggest driver for it is like the economic business case needs to just become more common. And I think as soon as that becomes readily apparent and we can act upon it, a lot of these things will take place pretty naturally. I think the most natural comparison that you can look to that with is the launch, like the launch market. I think SpaceX didn't just like do a singular thing and jump from 12 launches per year to the nearly daily cadence that they're at now. There's a progression over the course of about, was it 8 years at this point, maybe nine, of slowly, continuously seeing more viable business cases. In their case, the biggest driver is Starlink, um, into allowing them, hey, we just continue need to do more, which as a result, that sees all of the infrastructure being built around it, as well as the regulatory landscape kind of adapting to the specific things that they're looking for. And so from my perspective, the biggest driver in making return a really common thing is the world, and I think particularly the companies that exist that are doing it, kind of proving that there is a very real financial use case for that application.
Yeah. And so we have a picture in our mind, how big are these return vehicles that you're sending into space in size, and what's it look like when they come back? How fast are they going? Do they have a parachute? And
Yeah.
how do you choose where they land?
So this is, I think, an ever-evolving landscape between all of the different companies, et cetera. But I'll talk a little bit about how our system works. So our first one is scheduled to go up in the upcoming fall. The total vehicle is a little north of about 200 kilograms. Think about the dimension of the vehicle is on the order of, I think, just shy of about 50 inches. That is about, I'm trying to give that unit in meters as well, but a little over one, uh, about 1.25 meters, off the top of my head. Um, our entire system kind of gets launched into orbit just as any other satellite system does. So mainly the SpaceX rideshares are the biggest facilitator of that transport. They then orbit at on the order of about 500 kilometers altitude for, in our case, a couple of weeks to a couple of months. Subsequently, our internal propulsion system that is internal to the satellite puts us into a reentry trajectory. That reentry trajectory for us lands just off of the coast of Florida, where indeed a parachute will be deployed. It'll launch, it'll splash down under that chute, after which it'll be recovered and brought back to our facility, where the main intention at that point is to take stock of the status of the system, and it is intended to be refurbished and relaunched again at a later date.
Got it. And the speed in which it's coming back, it's getting over Mach 20.
Yeah, it's closing in on 30 in our case. We operate about Mach 29 on that order. That's not the exact number. So you're talking about like on the magnitude of about 20,000 miles an hour at that point.
Wow.
Because I think there is a certain amount of numbness that goes on with that, I think, as you can imagine. Because while on a physical level, Mach 22 to like Mach 28, 29, whatever it is a big difference in terms of potential energy. At some point, it doesn't matter anymore. At some point, it's just fast and you got to deal with numbers. Like they're, for all intents and purposes, from an observation perspective, it's like, yeah, that thing goes Mach 6 and the other one goes Mach 14. Sure, at some point it's just fast. It doesn't really matter anymore. Obviously, there's a lot of different applications, but yeah, from the human perspective, it's just unfathomably quick.
Got it. And are you seeing governments or defense agencies, playing a role in that early demand?
Yeah, I think, and this has kind of been a very common thing for the overwhelming majority of reentry vehicles, even though it's a relatively small market. But one of the big things that every reentry company, including ourselves, very quickly realize is, oh, there isn't a lot of stuff that goes that quickly. And so there is a substantial market that exists on the defense side related to hypersonics, related to seeing that things go that quickly and testing out either material or sensors and things of the like aboard those vehicles.
Got it. And would you say that's like, one of the main things that's growing the company and helping you reach, that next level where you have manufacturing be your main revenue stream? Is it starting with, the main customer being these defense agencies?
I think our vision for it is always a combination of the two, because they're really nicely complementary in the sense that they don't interface with each other all that much. Like when you can fly both on any given mission. For example, if you have one in our case where you are intending to fly, I don't know, let's say it's a hypersonic payload, that often is something that will find itself to the external of the satellite system or the entry system in this case. It's stuff that really wants to be exposed to all of that heat, all of that external pressure. And so you can fly that while simultaneously flying a internal microgravity research payload.
Got it.
But in terms of is it a substantial source of early revenue? Yeah, absolutely.
Yeah. And what would you say, there's a couple different things you can manufacture up there. Is there anything that you're focusing on specifically that maybe sets you apart?
I think on a high level, the most critical factor is every single branch kind of has some of its niches. But frankly, most of them, their main differentiation factor in terms of who they're going to want to fly with is cost related. Space continues to be really expensive. And so we have kind of intentionally taken an relatively agnostic approach to who and what type of sector and what type of microgravity payload we want to fly. Instead, we've said, hey, frankly, most of you all care about the same thing, which is that ever so important dollars per kilogram up and down. So let's see how efficient we can get that figure, because I think for almost all applications, that still continues to be one of and usually the most dominant decision-making factor.
No. And yeah, with new entrants coming to the space of the reentry market, you're coming into this space. This company is less than 2 years old.
Mhm.
Can you tell us the story? Just walk us through sort of that aha moment of what led you to go down this route and how you were able to grow and scale so fast to the point of you launching in a few months?
Yeah. So my co-founder and I started this a company as we were both finishing up our respective PhDs. And while we were doing so, we spent a lot of time working on reentry in the context, particularly for missions related to DoD mission sets as well as NASA ones. Um, we spent a lot of time within the reentry world, and I think one of the bigger frustrations from our end was that a lot of the engineering related to reentry missions is very, it's called conservative, I think is the way to say it. Usually when you do reentry, it is for a mission where you are either flying people or it is something extraterrestrial. It is by and large an application where the reentry is a thing that happens all the way at the end, and as a result has to take a very conservative approach, right? If you're returning a sample from Mars, for example, the reentry is not the part you're going to innovate on. You are just going to do what is prohibitively reliable, um, and make sure that that part of the mission succeeds. Because, oh my God, imagine that you fly something to Mars, land it there, scoop up a sample, get it back, and then it burns it, and then it burns and turns into a gas on its reentry to Earth. That's pretty terrible. And it's just not a scope of mission that you can deal with. And so what we very quickly kind of realized is we just can't believe that there is a much more optimal and efficient way to approach reentry. And kind of out of that motivation, combined with us starting to get more and more exposure to the stuff that's happening on the ISS, the microgravity research that happens there, we want to take a stand and kind of go, hey, we think we can approach this in a lot more efficient way. And out of that, we started the company, and now, what is it? A year, a little over a year and a half later at this point, we are a couple months away from launching our first mission, and if all is well, what will be the first we call a reusable satellite.
Got it. And you went through Y Combinator, is that correct?
We did, yeah, in the winter of 25.
Okay. Uh, Maybe tell us a little bit about that. What it was like being, a space tech company and
Yeah,
an accelerator environment that doesn't really
it,
look at hardware.
it's really interesting because I think, don't get me wrong, YC's focus very clearly is still on software. It is the thing that they do best, historically so. But I think particularly as you look at even taking a stock of a lot of the large space companies that are out there, it really baffled me to see how many of them are YC companies to begin with. And I think that still continues to be true. Like the number of space companies still kind of pales compared to the number of hardware companies, for that matter of fact, still pales compared to the number of software companies. But the infrastructure is still absolutely there. The network is still absolutely there. And I think one of the things that it forces you to reckon with that, especially our YC partner at the time was Michael Seibel. The thing that he kind of forced us to reckon with pretty quickly is that a lot of the things, a lot of the advice, a lot of the startup context that they give you, because you are quote unquote in space, because it's hardware, you kind of have the tendency to say, oh no, this doesn't apply to me. We are not like this specific. piece of advice or this thing is kind of difficult and it doesn't work for us, not applicable advice. And I think one of the things that the program, but especially like just the chats with your partner very quickly force you to kind of sit with is like, no, a lot of these things are basically standard. And while your timeline on a lot of those might still be different, frankly, they're still very accurate and there are still things that need to be followed. And so that kind of takes its form of like principles like, hey, like launch stuff early, make sure you get as much feedback as quickly as you can. Um, and stuff along those lines are just still very sound principles, even if they are slightly longer and more difficult to execute because you have to make a physical thing rather than ship some software. And so I think I recently saw a tweet from Gary Tan about this, which was like YC is the YC for space tech, and I do believe that to be true. And I think there's right your Stokes, Astronus, relativity, etc. Also show it to that effect.
Got it. And so many people apply for YC. Is there any like key storytelling that you had that made them say, this is, the company that's outside of our scope that we really want to bring in?
I I've been asked this question a lot. Like, why, right? How did you get in? And I think I get asked it in context like this as well as just by people that just approach me that also have similar ambitions of getting into YC. And I think the honest answer is that I don't really know. I've like sample set of like, are you getting in or not is one. And so I can't say that I know like, oh, this is why we got in. I can tell you a little bit about what at least our partner said, which was that after talking to us, he had at least now learned something that he didn't know before, which was in that case particularly focused on the whole microgravity research world, and that was apparently enough. Uh, Beyond that, I really don't want to present like I have the ability to give anybody that is trying to build a space company and get into YC be able to give them advice to that effect. I think my sample set is really just too small to be able to do so.
Yeah. I was wondering if you could give us an example, like a concrete example of a specific drug formulation where microgravity uh, changes the outcome enough to justify the launch and return costs. Like, what gets created up there? What does this
Yeah.
drug do? And
I
yeah,
think historically the example that has been used the most, because frankly it is a very large deal, is a initial version of Keytruda in its current form. It's a very large drug that was initially manufactured on Earth, and a more stable version of it, as I understand it, was identified on the International Space Station and subsequently recreated on Earth. It's an application where you're not per se doing the actual manufacturing it on orbit yet, because this is still right within the ISS era and all, but rather it is an application where Merck managed to find a different way to do that crystalline structure, and at that point introduce a new type of stability to that crystalline information and recreate it on Earth. And I think to date it has generated them a very large amount of money. Obviously, you can't attribute the entire success of that drug to just that part of the research, but having things like that within your toolkit can be a tremendous asset to a lot of pharmaceutical groups. I think a lot of the big things that a lot of people look at as to, hey, how can this truly be worth it on a manufacturing stage, relates to, right, what is the value density of a material? And so as we look at future drug discovery and their production, the main driver for all of those applications is like, if you can find a given material, and there are a lot of people that have the thesis that this exists, if you can find a given material where the value of said drug or sorry, not the value, sorry, where the existence of said drug is dependent on the absence of gravity. Let's say that it is a potential, I don't know, a potential cancer treatment within a given context, and you only need the chemically active component, which is milligrams. At that point, any given space flight can result in thousands of treatments within it, and that becomes a very natural cost point.
Got it. And what is the drug you mentioned?
Oh, it's Keytruda. I would have to.
What's that used for?
Right now, at least the structuring, it is the main application is HIV treatment.
Got it. And what's going on in your pod? Like, you think like a whole manufacturing capability? Is it like, it just needs to be in gravity and then heat up to a certain temperature and boom, you have the drug? Is it spinning it? Like, what's going
Yeah.
on in that return vehicle?
No, it's a very fair question. And so by and large, right, when you talk about manufacturing in this sense, usually, right, you get the concept of like, oh, we are flying right, robotic arms and an entire production process happens internal to something like that. But generally speaking, it is much less complex because the only thing that you are trying to do in space is the part that you absolutely have to. Which means that at least for missions that we currently have scheduled, that usually looks a lot more like it is usually a combination of mixing a specific type of fluids, for example, potentially heating it up. It is very basic operations. Like a really illustrative example is when people are trying to make a specific type of semiconductor substrate, for example. It is quite literally about mixing two fluids and then changing the temperature. Because everything else can happen in the presence of gravity. The only thing that you need to do is make that specific crystalline structure.
Got it. And, when it comes back and it's returned, what's it look like? Is it a liquid? Is it, like a block of just powder that was froze? And I'm
Um,
trying to imagine from what it looks like when you open it to then how does that go towards treatment?
it once again, it really depends on the application because in certain cases, right, we fly biologics, and in certain cases we fly crystals, but usually in the crystal structure case, yeah, it's really. Have you ever seen like a semiconductor like wafer?
Yeah.
That's what it looks like. It's just a more crude version of that that hasn't been pre-processed.
Okay. And is that like a concentrate? Can it be, divvied up into lots of different, doses for lots and lots of people, or is it still kind of a small amount?
It the problem with all of these is that it varies
It depends.
incredible amount, and so it depends, and so that it really depends on what specific. Because within our customer base, you have people who truly believe that they are intending on large scale manufacturing. Some of them intend to solely make what you'd refer to as like the seed crystal on orbit and then recreate it on Earth. Um, and so there's still a tremendously large dispersion in what the visions of this look like based from our customer set as well. And so if I already knew what the perfect approach was that was going to be successful in the long run, I would be doing that, right? That would be the part that we would immediately integrate. And so on a high level, we don't know what the correct approach is. We don't know what the successful approach is going to be. The only thing that we do know in the long run is that we really believe that this has the potential to change so many industries. And so we want to make a logistics infrastructure that can facilitate it.
Got it. Okay. So to build something that can withstand, Mach 29, as you're saying, like very, very fast, how do you actually build, what's it made out of, and how are you able to test it, make sure that, yeah, this is going to work when it's truly put up to that Mach 29 test?
Yeah, I mean the biggest part about any given reentry vehicle is its refer to it as its heat shield, right? And so you'll have seen a decent amount of stories about this related to the Orion capsule just feels a couple of weeks ago. I think it's even less than that. But making sure that our entire satellite does not evaporate on reentry is indeed like that's one of the main things that we do. And so for us, that looks like we make our heat shield in-house. I think we wanted to have as much control over that process as we could. I think the standard way to do this is to get something manufactured from NASA, and I think that works really well. It's got a tremendous track record. But I think, like I mentioned before, we wanted to pursue as much efficiency as we could here. And so we decided to produce that heat shield in-house. What it is a ablative, which means it's a specific type of material that burns away as it gets re-entered, at least for this mission and for now. Yeah, beyond that, there's not a tremendous amount to it. How you get to testing, there's a lot of ways to go about that. You can build a lot of things in-house. In our case, we opted to work together with NASA, who have a lot of test facilities that can recreate to a large extent the conditions that you go through during reentry. And so you can kind of test that for a very small sample of your material, and then beyond that, it's a lot of simulation. It's a lot of high fidelity CFD to make sure that that you then benchmark based on your physical test results, and that's kind of the only way that you can test it. Otherwise, the only way you have is to try it.
I'm curious what your sales cycles look like from the first conversation you have to actually, flying a payload. How does that work? Are you approaching people? Or are they approaching you? And, how do you select who's going to be a truly good customer and can get something out of this rather than someone who maybe just wants to try out, that's an experiment on something they're thinking of
I
that could
think
work?
it's a combination of both, right? We get approached, but we also, I think, especially in the early days, we approached a lot more people than we got approached, but that's kind of starting to change now. In terms of how we select people, I think our vision has always been to, be as agnostic as we can, which means if anyone has a payload that fits within the right parameters that needs the type of transportation service that we offer, we will always do whatever we can to fly it, independent of reoccurrence, etc. But we obviously like the groups that have the potential to fly a lot more missions better. In terms of what the sales cycle looks like, it varies pretty drastically based on how much experience that given group has. And so on the one hand, you'll have the groups that have a large amount of heritage on the International Space Station. They'll have flown, I don't know, 10, 20, or even way more missions aboard the ISS. And so they're very familiar with the process. They're very familiar with what they have to do. And so comparatively, flying with us has a lot less regulatory constraints attached to it. And for good reason, right? We don't have any astronauts on board. And so things don't nearly need to be as safe because, well, the ISS has one main priority, which is keep the astronauts alive. And that is much more important than any other research outcomes. But for us, that just isn't the case, right? We have mechanical stuff, which means if you want to, I don't know, emit a bunch of dangerous gas, you're not going to do anything to us. And so those types of groups we fly, that is a very relatively quick sales process. You're usually talking on the order of, say, weeks to a short number of months. The ones that are usually longer is when you're talking about groups that are unfamiliar with space, but wanting to start within it for a first time. There's usually a lot of explaining of what this process is even going to look like, them returning on their side, right? Looking at their entire engineering picture. And so those are things that are still continuously going
on. And how much of your value proposition is just, the we will handle everything and, you take it from there and they don't really have to do anything other than focus on their science or part of their manufacturing? Are you working with these companies like directly, or can you take an idea that they have, just sort of make it happen, create it, and deliver that product?
We've always kind of taken the stake in it of like we are not like we are not a research company in the sense that we don't have the bandwidth to do like help this specific group with expertise on their semiconductor substrate production. We don't have the expertise to then also help these people with their analysis of I don't know, neurodivergent diseases on a given type of organoid. Like the breadth of applications is much too wild on that front. So the thing that we've always done is we've always gone, great, what we can do for you is think of us as DHL or UPS or whichever other transportation group you want. You hand us over the specific thing that you want to go up and down, and we will provide that transportation. Well, obviously, right, we'll obviously do all of the FAA regulatory work, all of the compliance work with the launch provider, et cetera. But we're not going to do your science for you, or do your initial scale manufacturing for you, just because it's frankly just out of scope. And the nice aspect of the space industry and how it's been set up for is that there already is a pretty large industry just focus on doing that. The ISS would refer to it as implementation work, right? Helping people through that process and providing them with the hardware and or expertise to make their science a success. And so we collaborate a good amount with those entities.
What's stopping you from creating a reentry capsule that's, say, the size of one that would bring astronauts back?
In the short term, we believe that a lot of people are very much attached to their own flight schedules. And like, if you design something that flies astronauts, by definition, it is going to be a lot more capable and so also a lot more expensive. And so while it's absolutely something that I think is very awesome on a pure engineering and physics basis, I don't think it is as financially efficient to do it. And so is this something that we may potentially do someday? Yes. But our primary focus, certainly in the short term, is making sure that we can bring the entire up and down picture as efficiently as possible. And so that doesn't include people right now.
Yeah.
It's
Okay.
frankly keeping people alive is really difficult. Like in this between air pressure, foods, toilets, and like we saw that on Orion recently. It's yeah, that's a very tricky thing. And so we like how relatively simple it is without them.
Yeah. And you said these capsules, they stay in orbit for, a short amount of time. What's that time window look like? The days, hours, months?
Most of our missions are going to stay on the order of weeks to months.
Okay.
But that's not actually by limitation. That's usually much more by customer preference. We get inserted into a very stable, like LEO orbit on the order of somewhere usually between 500 and 600 kilometers altitude. So theoretically, we would have the ability to stay there for years if we wanted to. Certainly because we also have thrusters aboard, so we could even raise our orbit if we wanted to. It's just when a mission takes like, I don't know, let's say it's a couple of years, generally speaking, at that point, you're almost usually better off just flying a quote unquote regular satellite. Like there's not a lot of applications, at least not ones that are immediately obvious to us, that require something to stay on orbit for years and then return. Like most of the applications that we at least have been able to identify. And so once again, I could be wrong on this, but we don't see a lot of use for things to stay on orbit much longer than that.
And when you return, to Earth, like you said, this is off the coast of Florida. Like how accurate can you really be with this, and how far off the coast are we talking?
Think right now on the order of a couple tens of kilometers. That's about the scale that we're off, as well as the precision to within 3 standard deviations. Um, we are very much going to continue to pursue getting that precision down, of course. And so over time, we certainly expect to get a lot more precise in the area in which we can recover, just frankly because of our really short timeline. We wanted to make sure that we did the ocean now, just because at that point we would be able to get our reentry license on a shorter and expedited timeline.
Got it. And your capsules, they're reusable. They can do multiple missions.
Yeah, that is indeed. Sorry. I mean, there will be some refurbishment in between different missions, certainly at the beginning. But the entire um, philosophy from our side on how we can make this picture more efficient financially is focused around reusability.
So scaling up, does that look more like let's get a certain amount of these capsules built, and then we'll just have like them circulating all the time? Do you want to just keep on producing them nonstop? And would you sell these capsules to individuals for them to just have and they can run their own missions?
Uh, I'd say the answer is all of the above, right?
Okay,
Obviously, right?
that was a
As
lot of questions. Sorry.
Yeah, no, absolutely fair, and it's absolutely. But I think you're accurate on all fronts.
Okay.
I think yes, we are going to want to continuously reuse them over and over and over again, and so you're going to have a fleet that has a certain number of launchers in them, but you're simultaneously going to be continually manufacturing more, as we at least believe that the frequency will continue to rise quite aggressively. And then, are you ever going to sell them? I think we're very aware that there are specific customer sets, especially on the government side, that just won't accept not being able to operate their own systems. Um, and so that's kind of the end of that discussion. So yeah, we'll at that because we do want to work with those groups as well. Yeah, we'll let them operate their own systems for priority.
Got it. What would you say some of the big risks are as a reentry company? Is it technical? Is it timing or regulatory?
I'd say that the biggest one is still very much on the technical side. I
Okay.
think especially with that, I don't even mean obviously there is even with our first mission and subsequent ones, there's going to be a substantial amount of risk in like it's a first mission of a spacecraft. There is always a good chance that something is going to go wrong. But that is not actually the technical risk that I'm referring to, because I think that let's say mission one, something happens to go wrong, we have the ability to fix that, and right, we have the utmost confidence that that is something that we will be able to figure out. I think the biggest question from a technical perspective that we are going to answer over the next 3, 5, beyond years is the question that kind of launch had to answer as well, which is how cost efficient are you going to be able to be at making these things, right? Are the fundamental hardware is the fundamental hardware that you're going to have to integrate into this so expensive that the price doesn't come down enough to make this financially feasible? And that's the main question that we are trying to answer.
Got it. Yeah, with the technical side of things, is it more towards, actually being able to withstand that reentry, that force, that heat shield? Is it getting things to operate properly while in orbit? Maybe dive a little more into, what someone doesn't understand is so technically hard about this when they see it, just from a high level. If they were
Yeah,
to really understand it, I want to know what the hard parts really are.
sure. I'd say there are probably two, at least for our system, which is as a primary one, it is just physically doing reentry. When you right hit when you hit the atmosphere at around closing in on Mach 30, um, the atoms of the air can't get out of the way fast enough. And so as a result, they turn into an incredibly hot plasma that is about half the temperature of the sun. That's hot enough to effectively evaporate mostly anything. And so making sure that your system, one, with the shield is able to survive those temperatures, to continue to operate and do all of the subsequent operations, both from an electronics as well as a physical standpoint, correctly in with like very precise timing is tricky to say the least. Um, and so those requirements cause you to make a system that is not really similar to most other satellites. And those really complex requirements then kind of create difficulties when you're on orbit again, because it means that your entire system is kind of built to keep heat in and it's a really funky shape. And so there's a lot of both structural as well as thermal challenges with come that making sure that a system that is that integrated survives on orbit. Um, None of those are challenges that haven't been solved before, and they're challenges that we will be able to solve again. But that is the most complex thing from an engineering standpoint, as well as the fact that you never get to try anything twice. Sorry, you do get to try things twice, but there is a large gap between them. When you launch something, that is your attempt. You don't get to go up and quickly fix it.
Yeah. Yeah, just thinking about it, really being able to be sure these things can withstand returning into going through the atmosphere, going, 20,000 miles an hour. I mean, what kind of tests are you running on this thing?
So the biggest ones, like I said before, are with NASA, particularly on the heating side of it all. And the problem with how extreme these environments are in these contexts is there is just a very limited amount of testing that can physically be done. Like there isn't I don't know, the equivalent of a wind tunnel, except like 10 times as fast or 30 times as fast, even at that point, that you can just put your entire spacecraft in and go, please turn it on and make sure that it works. Like the best thing that you've got for recreating that environment is for a piece of material that's like this big. And from that point on, it's a lot of simulation.
Okay.
And obviously, there's a lot of testing that you can do otherwise for like the space operations part, things like vibration tables, thermal vacuum chambers, etc. But that's pretty standard for any satellite. The reentry part of it really doesn't have as much testing capabilities as you would want it to. But there just isn't an answer for that.
Got it. What do you think the future is going to look like in this industry? There's a lot of new players with reentry capsules, very few who've actually flown. Is it going to be a winner takes most type future, or do you think it'll stay pretty fragmented for a long time?
I think there will absolutely be a winner that takes the majority of particularly the large mass contracts and the large mass customers in there. Um, just because pretty similar to the launch space, most people are not really as selective as they would like to be. Their main driver is still cost and availability, which is why SpaceX works, right? Their stuff works. It's cheaper than effectively anybody else's, and it just is there so frequently that it's really hard to say no to. But simultaneous to that, Rocket Lab, Firefly, etc., still have a lot of applications within more specific requirements contexts. And I think that the same thing is going to exist within reentry. I suspect that there will be one, or at least a very small number of players that'll exist on a much more larger scale, higher frequency basis. But there'll be a lot of return vehicles as well that'll exist for more niche applications.
No. Can you tell us a little bit about some of the milestones you've hit up until this point and besides the flight in the fall, what other milestones people should be looking out for?
Yeah, on a very high level, our main our main and most important milestone is everything related to that first spacecraft, right? It is getting the full system, getting through all of the testing of all of the respective subsystems, as well as now going through the final integration, and very soon getting the full system on the full system vibe, getting that done to make sure that we are okay to launch with SpaceX. That is the most important and primary goal. And as we continue over the next couple of months, the biggest milestone from our side will be, hey, the thing goes into orbit. Hey, the thing orbits well, and then it comes back. Um, Beyond that, we now spend a lot of time starting to schedule our subsequent missions, right? Getting the second, third, and beyond on the books with the respective customers as well. And so the biggest push from our side over the next couple of months is really going to be about ratcheting up the cadence and the infrastructure that we need from our side to enable that.
Oh, very nice. And for people listening to our conversation, if they were to walk away after hearing this chat with, one big thing, what would you want that takeaway to be for them?
I think the main one is that on a very high level, like reentry is going to start playing a much bigger part of the space economy. Um, and so we don't know what a lot of those physical implications are going to be about what kind of industries that it is going to enable, especially for those that are more space inclined. I would love for them to think about it, and let's find out over the next couple of years.
Yeah, absolutely. Okay. Well, Steph, this has been a fantastic conversation. I'm really excited to see your guys' first launch and see, what you're doing in the future. It's going to be very exciting. Um, do you have an exact date for the launch in the fall?
We don't. Unfortunately, SpaceX works with launch windows
Okay,
as does everyone else. But yeah, we should get a little bit more detail on that in the next couple of months. But the current launch window is no earlier than October.
got it. I'll mark my calendar. I'll make sure I'm following you on LinkedIn and all the updates as well.
Absolutely. All right. Really appreciate it.
Thank you so much. Thank you, everyone. Take
Yep.
care.
Bye.